issue. So, you see a lot of simple stories about this, but I think the thing to remember is that this is a complex issue. So there have been some attempts to do a cost-benefit analysis, and these are some of the key ones. There was a thing funded by the UK government called the Stern Review. They came up with an estimate, the annualized net present value of damages, almost 20% of gross domestic product, and the cost of achieving a 450 ppm CO2 was 1%. So that conclusion was, it's like a no-brainer. Why wouldn't we do this? And they believe that CO2 emissions would need to fall from 7.5 gigatons today to about 2 to 4. Bill Nordhaus at Yale University has been doing this work for a long time. He does this whole model, which is an optimal cost-benefit general equilibrium model, essentially. His argument is that the optimal CO2 price today is about $10 a ton, and that would allow temperatures to continue to rise to 3.5 degrees by 2100, and emissions would continue to rise to 7.5 to 11. So his idea of what's optimal is to continue to increase emissions, reduce them a little bit from what they might have been. So those are kind of two of the, you can see the extreme ends you get from that's not even the extreme end. Richard Toll, who's an economist in Europe, suggests that the current social cost of carbon is almost nothing to about $27 a ton, and that is comparable to Nordhaus's estimate. So he points out that it depends on whether you care what happens only in your country. So do we care what happens to the rest of the world? Do we place that in part of our valuation of carbon, or only about ourselves? How do we value effects to other people? Then Marty Weissman's an economist at Harvard, he's really gone into this deep uncertainty issue, and he points out this problem really is one where there's deep uncertainty, and when you have that, you can get a problem which is called distribution has fat tails. When the distribution of a problem has fat tails and losses get very large, you're multiplying a loss that's growing towards very, very large times a probability that isn't vanishing. The nice thing about our normal distributions are the probabilities go to zero as we go out in the tail, and so then it's not important. But when you have this probability not vanishing and you have losses getting very large, that sort of very small probability, less than 1% times a very catastrophic result, can dominate the whole cost-benefit analysis. So much attention in this problem is focused on the median case, or what's happening in the middle of the distribution, which, frankly, some of those estimates have showed it not to be so bad, as you see here from the Nordhaus or Toll stuff. But if those things we can't even hardly speculate about are out there and contributing to this fat tail, that's what we ought to be concerned about. And sort of focus on just the part we know about is to focus on, is to use the old metaphor, looking under the street lamp. You said the fellow said he lost his driver's license, and he's searching around under a street lamp, and someone says, "Did you lose it here?" He goes, "No, I lost it somewhere else, but the light is better here." So that's a little bit, by focusing on the middle of the distribution, we're not focusing on where we really have to focus in order to understand what the problem is. So, that leads us to the other issue, as I mentioned a little bit earlier, policy design. This cap and trade versus pollution taxes. Those are some of the two economic stories you'll hear people talk about. Economists worry a lot about that. We'll talk about this more if you have some questions. What are the role of other measures? The role of R&D. And then, this whole game theoretic problem of, if we act, will China act? Will India act? How do we kind of think about the solution to that problem? So that becomes relatively important. So with that kind of background, I want to turn a little bit to some of the work we've done. We try to look at the uncertainty of this problem, and we've done this very big Monte Carlo uncertainty analysis. This slide just says it takes a long time. It's a big computer effort to do these. It took 6 or 8 months of computer time, a 64-node computer cluster running. So it's simulating our model many, many times to kind of represent this distribution of outcomes. There was a federal government climate change science program exercise on scenarios. We followed that. We have a ensemble with no policy, what will happen if you don't have any climate policy, and then one looking at different levels of climate policy. So this is what we turn it into, and this has turned out to be a relatively useful device to kind of represent the problem. I'll tell you how we came up with this originally. We did this is the second round of this. We've done it back in around 2003, and the Wall Street Journal was interested in running a story about this thing, and we had a probability density function that we showed them, and they said, well, our readers will never understand that. And I think this is a story that maybe explains a lot of what's happened in the financial markets the last few years. So we came up with this roulette wheel, and the Wall Street Journal said, yes, our readers will understand that. So one would hope that the people in financial markets would have understood probability a little better, but apparently the gambling did more with it, how they think about investing money. So as you see, this no policy case is generating, we think there's a chance of, the median of this is like 5.2 degrees warming. That is really a lot of warming. I mean, this is much, much more than we were expecting a few years ago, and I think I have a slide here that shows you what our result was a few years ago. And so a significant chance of even greater than 7 degrees. People think that if we get 2 to 3 degrees of warming, when you had paleo history like that, that's when you had, ice-free Greenland and ice-free West Antarctic, so you have meters of sea level rise associated with that potentially, even at as little as 2 to 3 degrees. But if we go on with this no policy, we find, just a little slice that's less than 3 degrees, and most of it above that. So people don't know how fast the ice sheets would melt. They might be hundreds of years, but if we get into these temperatures, we're almost certainly over time melting the Greenland ice sheet, the West Antarctic ice sheet, and that's a massive effect on it's meters and meters of sea level rise. If we took this policy, then you see this is stabilizing CO2 now at 550 parts per million. We're getting down to safer levels, but even those aren't that safe. The Europeans have called for a 2 degree target, but they actually are calling for a 2 degree target above pre-industrial. This is temperature by 2100 above today. So since we've already experienced 0.6 to 0.8 of degree warming, if you added that onto this, you see that only in that darkest blue one, 1 to 2 degrees, would we really be staying below 2 degrees, have a chance of staying below 2 degrees from pre-industrial. So the challenge in this issue is fairly great. And even if we control emissions, we still don't understand the system, so there's still uncertainty left in it. I don't have the slide in here that shows comparison to our old work, but frankly, the old work, the no policy case looked more like the right side of this, and so it's just over the past 5 years, our understanding of this problem has led us to be far, far more concerned than we were a few years ago. So it just has, I think the science has just been coming together, and it's really been fairly shocking. It was fairly shocking for us when we first came up with these numbers. We went over them many, many times, wondering where we made a mistake. It turned out really that, we were several revisions in the estimates, all were revised toward leading to a warmer result. No one of those things were tremendously big on their own, but they actually interact in a multiplicative way. So in fact, the whole problem really exploded and doubled our estimate of the median temperature change. So we do a whole set of estimates of trying to estimate the climate sensitivity and ocean heat uptake by constraining the model with observations of temperature. The ocean temperature stuff suggests the ocean was slower than we thought, taking up less heat, so that was causing more warming. We reduced our emissions of aerosols that are cooling the atmosphere because people are trying to clean up aerosols. That shut off some of the cooling phenomena. We had a little bit more feedback from terrestrial vegetation. We looked at things like emissions in China and India, which were growing more rapidly than we thought. you put those things together, and we just got this very large increase in the